You're standing over a workbench, looking at a printed plan. The outline is clear. The structure makes sense. But a few key measurements are missing. A width is implied but not stated. A spacing looks consistent, but no number confirms it. And suddenly, something simple turns into a chain of uncertainty. Most project plans rely on a hidden structure of completeness. When everything is present, the process feels linear. You measure, cut, assemble, and adjust. Behind that simplicity, there's an expectation that the information has already been verified, standardized, and tested. The plan becomes a shortcut between idea and execution. In everyday situations, this works because of a larger system. Designs are often created using software, tested in controlled environments, and refined through iterations. Measurements are usually based on standard material sizes, common tool capabilities, and predictable tolerances. There's an entire chain behind a simple diagram, even if you don't see it. But when part of that chain breaks, the experience changes. A missing measurement means the plan is no longer self-contained. You are no longer following instructions. You are interpreting them. And interpretation introduces variability. If one dimension is unclear, it can affect alignment. If spacing is inconsistent, it can affect load distribution or stability. Small gaps in information can compound as the build progresses. By the time you notice the issue, materials may already be cut, limiting your ability to adjust. To deal with this, people tend to rely on a few broad approaches. One common method is inference. This means looking at the surrounding measurements and trying to deduce the missing value. If a structure appears symmetrical, you assume equal spacing. If a component aligns with a standard material size, you estimate based on that standard. This approach is quick and often works for simple builds, but it depends heavily on pattern recognition and experience. Another method is proportional scaling. If the plan includes a reference dimension, you can scale the rest of the drawing accordingly. This is often done using printed plans or digital images, where you measure directly on the diagram and convert those measurements into real-world values. This works best when the drawing is accurate and not distorted, but small errors in scaling can lead to noticeable discrepancies. There is also the approach of mock assembly. Instead of committing to final cuts, you use temporary positioning. You place components loosely, adjust spacing visually or physically, and then mark the final measurements based on real alignment. This reduces risk but takes more time and may require extra materials. A more structured approach involves creating a reference system before building. This means establishing baseline dimensions, such as total width or height, and then dividing that space into equal or functional segments. Instead of relying on the plan for every detail, you define your own measurement framework based on the intended outcome. Within these categories, there's a specific format that becomes especially useful when plans are incomplete. It's the use of derived measurement systems built directly from the materials and components you have. Instead of asking what the plan intended, you start by asking what your materials allow. You measure the actual width of your boards, the true thickness after milling, and the spacing required for your tools or hardware. These real-world values become your primary reference. From there, you rebuild the missing parts of the plan step by step. If spacing between slats is not defined, you calculate it based on total width minus material width, divided by the number of gaps. If a support position is unclear, you place it where it provides structural balance rather than where the plan vaguely suggests. This approach changes the role of the plan. It becomes a visual guide rather than a strict set of instructions. Functionally, it works in a sequence. First, you identify all known dimensions. Then, you map out the unknown areas. After that, you define constraints based on materials, tools, and intended use. Finally, you calculate or physically test the missing measurements within those constraints. What makes this different from traditional plan following is that it shortens the dependency chain. You are no longer relying entirely on the original designer's completeness. You are integrating your own environment into the build process. This format is often used in two ways. Some people apply it informally, adjusting as they go. Others follow structured guides that are designed around this concept. These guides typically include a full materials list, but also explain how each measurement relates to real components. They may show assembly layouts that adapt to different sizes, and sometimes include notes on spacing, alignment, and load handling. In some cases, they also describe how to set up basic systems, like simple jigs or alignment tools, to maintain consistency during the build. The focus is less on exact numbers and more on repeatable relationships between parts. This kind of approach can be useful for people working with limited or inconsistent plans. It also helps when materials vary or when tools are not perfectly standardized. Instead of forcing the build to match the plan, the build evolves from the available inputs. It's not a replacement for detailed plans. When complete information is available, following it is usually faster. But when gaps exist, this method provides a way to continue without guessing blindly. It reduces reliance on external precision and brings more control to the builder. The structure becomes something you actively define, rather than something you passively follow. For those exploring this approach further, there are structured guides that document the process step by step. These guides typically show how to move from incomplete plans to a fully defined build using real measurements and practical constraints. One example of this format is often referenced in the video description for those who want to examine how it works in detail.